Have you ever walked right up to a 4K TV and pressed your face near the glass? From the couch, the image looks like a perfectly smooth, continuous window into another world. But if you look closely enough, that smooth illusion breaks down into millions of tiny, rigid blocks of color. For thousands of years, classical physics treated the universe the exact same way we look at a TV from the couch. Scientists like Isaac Newton viewed reality as a continuous, seamless painting where energy and matter flowed smoothly and could be divided into infinitely smaller pieces. But it turns out, the physical universe actually behaves like the TV screen. If you zoom in far enough on reality, things stop being smooth. At the microscopic level, the universe is pixelated. Realizing the universe had a resolution limit meant that energy couldn't be divided into smaller and smaller pieces forever. It came in fixed, indivisible units, providing the foundation for every piece of modern technology we use today. The first physicist to zoom in far enough to hit the universe's resolution limit was Max Planck. This animation illustrates exactly what Planck discovered. Notice how the continuous, flowing wave suddenly breaks apart into distinct, separate blocks. Planck called these unbreakable, individual packets of energy quanta. They are the literal pixels of reality. This discovery birthed an entirely new field, quantum mechanics. Quantum mechanics is simply the study of how these discrete energy pixels behave. When Planck mapped out these pixels, he proved that the everyday laws of physics, the rules governing a thrown baseball or driving a car, completely break down and stop working at the microscopic level. A few years later, Albert Einstein took Planck's code and expanded it. He proved that light itself is a storm of pixel bullets called photons. Photons are discrete, indivisible packets of electromagnetic energy. Niels Bohr took this pixel concept and applied it to the very structure of the atom. In Bohr's model of the atom, the orbiting electron is locked into a specific lane, unable to exist in the space between tracks. When it absorbs energy, it performs a quantum leap, instantly teleporting to a higher lane without crossing the space in between. Atomic matter behaves exactly like a video game character snapping to a fixed grid. It completely bypasses the concept of physical travel distance. As scientists looked closer, physicists like Werner Heisenberg and Louis de Broglie began discovering severe bugs in how the universe operates. One bug is wave-particle duality, a physical glitch where particles act like solid objects one moment and expanding ripples of water the next. Then came Heisenberg's uncertainty principle. The uncertainty principle is a physical law stating that it is impossible to know both the exact location and the exact speed of a particle at the same time. Think of it like a computer graphics card struggling to render a fast-moving object. If the universe uses all its processing power to capture the exact speed, the location gets blurry. If it focuses on rendering the exact location in high resolution, it loses track of the speed. The engine forces a physical trade-off. This means that at its deepest level, the universe does not have fixed, knowable states. It is built entirely on probabilities. In 1927, leading physicists gathered to argue over these glitches at the exclusive Solvay Conference. Einstein rejected this probabilistic universe, declaring God does not play dice. Bohr radically countered, telling Einstein to stop dictating the rules of the universe. The scientific community ultimately sided with Bohr. Predictable, clockwork physics died at that conference, and the modern probabilistic worldview took its place. So why should a high school student today care about a physics argument from the 1920s? Because early experiments on these very theories moved humanity away from passively observing the universe and allowed us to actively engineer it. By mastering Bohr's quantum leaps, scientists realized that when an electron drops from a higher lane to a lower one, it releases a single photon of a very specific color. By packing millions of electrons into the same high-energy lane and triggering them to leap downward at the exact same instant, scientists created a perfectly synchronized flood of light. This is the exact mechanism that created lasers, powering everything from barcode scanners to Face ID. Mastering these microscopic rules turned the unpredictable nature of atoms into a reliable, programmable tool. This schematic illustrates a transistor. A transistor is a microscopic semiconductor device used to switch electrical signals and power, built entirely on controlling the unpredictable probabilities of electron behavior. By trapping these quantum ghosts, transistors act as the microscopic brain cells that drive all modern computing. Billions of these microscopic quantum gates are hardwired directly into the smartphones and internet infrastructure you use every single day. By building machines that account for the pixelated nature of reality, we moved from observing nature to directing it at the scale of a single electron. If you enjoyed exploring the foundations of the digital world with us, drop a like, subscribe to the channel, and let us know in the comments what universe glitch you want us to explore next.